All right, welcome back to the second part of our video series for using moles to perform unit conversions in chemistry. I wanted to start by coming back to explain something maybe a little bit more clearly about the last problem that we worked on, the first part of the video. If you remember, we were looking at this problem asking how many formula units there were in 6.17 moles of aluminum chloride. And then we extended that to ask a slightly more complicated question, which is what would be the mass of those chlorine atoms in this many moles of aluminum chloride. And I showed you one way to do the unit conversion, which is a little bit longer. A shortcut that you could take, and is based on this recognition of the similarity between these conversion factors really, is to understand that if I have a mole of some compound, okay, whether it's aluminum chloride in this case, or maybe I have a mole of water, or a mole of, let's take something slightly more complicated, sodium sulfate, that in 6.022, okay, and times 10 to the 23rd, in 1 mole of these particles, there are 3 particles of chlorine for every particle of this compound. And so really what that means is that I have 3 moles of chlorine in every mole of this compound, okay, in this case. And so I can actually use this conversion factor to do that conversion to find the mass in grams. And I can sort of skip a couple of steps from the way I previously showed you to do this. All right, so it's just this ratio really between the elements, the number of elements in each compound that I can express in this way. If I have a mole of the compound, then I'm going to have conversion factors which are based on the ratio of number of one type of atom to some other type of atom. So here I have, if I have a mole of this, I have 3 moles of chlorine in that mole. If I have 1 mole of this, I have 1 mole of aluminum in that mole of aluminum chloride. If I look at water, for example, if I have 1 mole of water, that means I actually have 2 moles of hydrogen per mole of H2O. Because really what I'm doing is I'm just saying, well, in a mole of H2O, there are 6.022 times 10 to the 23rd molecules of H2O. And in each one of those, there's 2 hydrogen atoms. So I'm multiplying that number of moles by 2, okay? And so I have 2 moles of hydrogen per mole of H2O. If I had 3 moles of H2O, then I would multiply that number by 2. So I would have 6 moles of hydrogen in 3 moles of H2O, and so on. In sodium sulfate, I have 2 moles of sodium for every mole of sodium sulfate. I have 4 moles of oxygen for every mole of sodium sulfate. And I have 1 mole of sulfur for every mole of sodium sulfate. So I can use these as conversion factors if they are convenient for the conversion that I'm trying to perform. So that's something useful to keep in mind. It will allow you to make some of these conversion problems shorter if you can recognize this. So let's go back and rework this problem that we did last time and that we correctly found the answer to using a longer process, but let's use this conversion factor between so for the ratio of the number of moles per mole of the elements here to see how this can be shortened a little bit. So if I have 6.17, excuse me, this is supposed to be moles of aluminum chloride. If I have 6.17 moles of aluminum chloride, and I want to find out, well, how many grams of chlorine are in those 6.17 moles? Well, I can convert to moles of chlorine first using this conversion factor. In 1 mole of aluminum chloride, because of this ratio, I know that I have 3 moles of chlorine atoms. And then it's just a matter of changing moles of chlorine to grams of chlorine, which is what we really want. So I still need this same conversion factor that we used last time, which tells me that a mole of chlorine is 35.45 grams of chlorine. Okay, again, this is just the molar mass. It's the mass per mole of chlorine. And if I compare this now to what I had last time, you'll see that the effective multiplications that I'm doing are exactly the same, in fact. So here I have 6.17 times 3 times 35.45. And in the way we did it previously, these two factors ended up canceling, but I still end up with 6.17 times 3 times 35.45. So I will get the same result at the end of the process. All right, so this is a little thing that you should be aware of that you can use to take shortcuts, and in some problems it may even be necessary to recognize this relationship. If you have questions about that or if that's confusing, please let me know. Okay, coming back to continue some more of these problems of conversion. So 12E in the chapter review is asking us how many moles of, okay, again, let's practice identifying the chemicals here. I should recognize that this is a sulfate ion. So this is a polyatomic ionic compound. And so its name is going to be named after the individual ions involved. So we have sodium as the positive ion and sulfate is the negative ion. So this is sodium sulfate, but this is a hydrate. It's got water molecules bound up in the crystal structure of this compound. And I have 10 of them. So this is sodium sulfate deca, it's the prefix for 10, decahydrate. So how many moles of sodium sulfate decahydrate are in 8.99 times 10 to the 24th formula units of sodium sulfate decahydrate? So again, we start by writing what we know, what we're given. 8.99 times 10 to the 24th formula units. Very fun to deal with formula units of sodium sulfate decahydrate. Again, I'm being very careful to be complete here because this might end up having implications in the future. And in 1 mole of this, I know that I have 6.022 times 10 to the 23rd particles, formula units. Okay, but so I want moles. So for now, that gets me where I want. I can do this conversion. And when I multiply these, I'm going to come up with the final value of 14.9 moles. Okay, or 1.49 times 10 to the first moles of sodium sulfate decahydrate. Okay, you may be wondering why I have all of this over here. Here I was just showing a breakdown of, again, how we would find the molar mass of this. Now, we don't need the molar mass to find the number of moles because we just have this conversion factor with Avogadro's number. But what if I were asked instead to find how many grams, or the mass of this amount of formula units of sodium sulfate decahydrate? Well, in that case, I'm going to need the molar mass conversion. So you can see here, I'll find the molar mass by multiplying the number of sodium atoms in each formula unit by 2, since there are 2 of them. The sulfur atoms, there's just 1 of those, so I just add that atomic mass. There are 4 oxygens from this, and then 10 oxygens from this. So I actually need to either multiply 16 by 14 or add them separately, do 16 times 4 and then 16 times 10. And then there are 20 hydrogens. Okay, sometimes students will miss this. There are 2 hydrogens in each water molecule, and then there are 10 water molecules, so there are 20 hydrogens total. And if I add up all of those atomic masses, I will get 322.2 atomic mass units per formula unit, per single formula unit of this, which means that the molar mass is 322.2 grams per mole. So if I want to find the number of grams, that's the conversion factor that I'm going to need to use. So I continue this conversion. Again, I'll abbreviate this a little bit here just for the sake of time. I won't write out all the units in such detail, but we're going to have the same setup up to this point. And then we're going to use this conversion factor. All my units will cancel. And we will end up with this number, which I pre-calculated. But we keep 3 significant digits, so we're going to actually have to round this a little bit. So we're going to get 4.81 times 10 to the third grams of sodium sulfate decahydrate in 8.99 times 10 to the 24th formula units will give us that much mass. Okay, so there are 2 examples of how to go from formula units either to moles, so 1 step on the bridge, or to grams, so 2 steps. Okay, just 2 more problems to look at. This is exactly the same sort of problem as the last one we just did. What is the mass of this many formula units of now this compound? Now again, let's think about the name of this. If I have memorized by ions, I should recognize that this is ammonium, this ion, NH4 plus, and this ion is it's a little bit more rare. This is not one of the main ones that we need to focus on so much, but again, it's in your book in the table for oxyanion ions. This is oxalate, C2O4 2 minus. So this compound is ammonium oxalate, and it's a hydrate, but we only have 1 water molecule per formula unit in this case. So it's just ammonium oxalate monohydrate in this case. Okay, again, if I want to find the mass, excuse my pens rolling all over the place. If I want to find the mass, I'm going to need the molar mass, okay, which again I find by adding up the number of atoms and their atomic weights in 1 formula unit of this compound. So I have here, let's just go through the counting again. I have 2 nitrogens, so 2 times the atomic weight for nitrogen, atomic mass for nitrogen. I have 10 hydrogens. Now it may not be immediately evident why it's 10, but if I look at here, I have 4 in each ammonium. And then I have 2 ammoniums. So that's 4 times 2. That gives me 8. And then I also have 2 hydrogens from the water. So that's 10 total. So I need to multiply the atomic mass of hydrogen by 10. I have 5 oxygens, 1 from the water and 4 from the oxalate. So 5 times 16. And then I have 2 carbons from the oxalate. 2 times 12.01 is the atomic mass of carbon. And when I add all of those, I get 142.1 AMUs. Which means, again, that the molar mass that I'm going to use for the conversion is 142.1 grams per mole of this substance. Okay, so let's go through it now that we have the conversion factors that we need. 2.51 times 10 to the 23rd formula units of ammonium oxalate monohydrate. And there are 6.022 times 10 to the 23rd of those in 1 mole of this. Then there are 142.1 grams, 142.1 grams of this substance per mole of this substance. Again, my units will cancel. And I will be left with, when I perform the conversion, the multiplications and the divisions, again, I have 3 significant digits. I will end with this number, 59.2 grams of ammonium oxalate monohydrate, or in scientific notation, 5.92 times 10 to the first. Okay, final example for now. Okay, this is about as tricky as any of them get. But if you keep your wits about you and you remember what percentage really means, this is not undoable. So we're being asked here, how many hydrogen peroxide? Okay, this is a very interesting and special compound that is used a lot in chemistry and in daily life. In fact, you probably have this in your medicine cabinet. How many hydrogen peroxide molecules are in 5.08 liters of 3% hydrogen peroxide purchased at the pharmacy? Okay, the fact that it's purchased at the pharmacy is completely irrelevant to the problem. It doesn't matter where you got it. You could have, stolen it from your neighbor or found it on the street corner. It doesn't matter. The important, for the math here, the important thing is that we have 5.08 liters of it. It's hydrogen peroxide, and it's 3% hydrogen peroxide. Okay, so what 3% means is that this hydrogen peroxide is not pure hydrogen peroxide. It's been diluted, it's been dissolved, it's been mixed with water. And so 97% of that 5.08 liters is just water, in fact, and only 3% of it is hydrogen peroxide. Hydrogen peroxide is relatively unstable as a compound, so if you had 100% hydrogen peroxide, it's relatively dangerous. And it's not typically the type of concentration you want to be dealing with. You can basically bleach everything, sort of eat your skin and so on. So 3% will still do this, but in a much more controllable and limited way. It's not super dangerous to use 3% hydrogen peroxide. If for more industrial type applications or for some chemistry experiments that we could do, we might use as high as like 35%, but to go beyond that is starting to get a little bit too dangerous for our purposes. So again, we take what we are given, okay, to start with in this unit conversion. I have 5.08 liters of hydrogen peroxide. Okay, now we haven't done anything with liters before, and liters is a volume, not a mass. So this is a little bit different, but we're told that the density of hydrogen peroxide is 1 gram per milliliter. So we do have a conversion between volume and between mass, because milliliters are just, there's 1,000 milliliters in a liter. So to use this, we're going to need to go to milliliters first. So in 1 liter, we have 1,000 milliliters. That's our first conversion factor. Okay, and then so we can change this into a mass using this density. Okay, remember, density is, if you remember the formula, density is mass per volume. Okay, it's mass over volume. And that's exactly what we have here in terms of the units. So we have a mass unit, this is just a conversion factor, in fact, a density. We have a certain amount of mass per a certain amount of volume. Here we have a volume, and we can cancel this now by using that density, 1 gram per milliliter. Okay, so this will, thus far, we'll have a certain number of grams of hydrogen peroxide. Now, where does the 3% come in? Well, this is, the 5.08 liters, that's 100% of the volume. That's the water and the hydrogen peroxide and everything mixed together. Remember, percent is a ratio. Okay, just like all these conversion factors, these are ratios, whereas these are 1 to 1. So like 1,000 milliliters is exactly the same thing as 1 liter. Or the density here is exactly 1 gram per 1 milliliter. But this hydrogen peroxide is 3%. So that means 3 out of 100, basically, right? If I take that fraction and I convert it to decimal, it's 0.03, which is equivalent to 3%. Hope you can see this. This might be too small. Let's write it over here. 3% equals 3 out of 100. Well, 3 out of 100 what? We're doing unit conversions here. Well, it's out of the total mass or the total volume or whatever. So it doesn't really matter. I could use milliliters here, or I could use grams. It doesn't make any difference really. I'm going to go ahead and use milliliters. So in 100 milliliters of this solution, 3 of them are going to be hydrogen peroxide. 3 of those milliliters will be basically pure hydrogen peroxide molecules in terms of the total volume. And so I have this conversion factor. This is where the 3% factors into my equation. Because so far I just have the mass of all of it, okay, the whole solution. I haven't yet taken into account how much of it is hydrogen peroxide versus how much of it is water. So I have 3 milliliters of hydrogen peroxide per 100 milliliters of, we'll just say solution for lack of a better term here. Okay, the solution is both H2O2 and water put together. Okay, so now I have the number of grams of actual hydrogen peroxide, and I want to know the number of molecules. Okay, so right now I'm in grams. I want to get here to number of particles or number of molecules. So I need 2 conversions working back this way. So again, I need a molar mass. And again, I've already pre-calculated this here, okay, in the same way as the previous examples. There are 34.20 grams of hydrogen peroxide per mole. And I put grams on the bottom this time because I'm working the opposite direction from the last couple of problems. So that cancels these grams. And now I have moles of hydrogen peroxide, and I just need one more step. So now I want to go to number of molecules, and we know that in a mole there are 6.022 times 10 to the 23rd molecules, or particles. Okay, and now I have the unit that I want. And when I do this multiplication and these divisions, I will end with this number, 2.70 times 10 to the 24th molecules of H2O2 in 5.08 liters of 3% H2O2. Okay, this is not the total number of molecules, again, of all of the molecules in the solution. This is just that 3% worth of H2O2 molecules. Okay, there are many more molecules of water because remember, the rest of the solution is 97% water or something else, depending on what you're mixing it with. And so, this is not telling us the total number of molecules in 5.08 liters. This is telling us how many of those molecules total are actual hydrogen peroxide molecules. All right, that's it for the examples. I'll be sending an assignment later in the week with some problems like these for you to work on your own. Again, please ask questions through email or text or phone call if any of this is confusing to you. Next video, we will look at the difference between structural, empirical, and molecular formulas.